Welcome to ENSS 135, Global Change, the Science and Policy of Global Warming. I am David Carrard-Howery, and I will be your professor for this course. We're going to spend the next several weeks talking about and modeling how greenhouse gases affect the Earth's climate. In order to do that, we'll need to start by understanding radiation. Hopefully a lot of this will be reviewed, but don't worry, by the end of the video we'll be putting up some fun equations that you've probably not seen before. Essentially, everything that has a temperature above absolute zero radiates energy along the electromagnetic spectrum. You're used to that when it comes to heat. You can feel the sun radiating energy across the void of space, and you've probably felt heat radiating through the glass panes in a fireplace. But even cold things radiate energy. You just may not notice it because the energy that they radiate may be less than the air that's constantly radiating energy in your direction. When something radiates energy, photons, little quantum mechanical packets of energy, leave that thing as a wave that radiates outward in all directions. When you feel radiated heat, that's because you're absorbing those photons. The electromagnetic spectrum is a gradient of the energy of the photons that radiate away from an object. We're all familiar with the spectrum of visible light when you see a rainbow or from a prism. Due to refraction, the prism separates photons by their energy, so that the lowest energy photons that we see, things like reds and oranges, are on one side, and then come higher energy photons like yellow, green, blue, indigo, violet. If we were bees, we could see more colors with higher energy than violet. We call those ultraviolet. We call the region of the spectrum with just a little less energy than red infrared, and we often think of it as heat because it's the part of the spectrum where things that are warm but not hot enough to glow in the visible range, it's where they emit energy. So mice, for example, radiate in the infrared region of the spectrum. Rattlesnakes can see photons with less energy than red, so rattlesnakes can see heat, and they can use that power to track down unfortunate mice. If we expand out the spectrum, we can see a lot of types of radiation that share the spectrum with light, but that we may not think about like light. For example, microwaves, radio waves, on the other side X-rays, and so on. It's useful to think about the amount of energy that a photon has in a quantitative way. You'll often hear people talk about wavelengths or frequency. The way I like to think about it is to remember that all photons travel the same distance in a given amount of time, that's the speed of light, but higher energy photons do a lot more vibrating along the way because they have more energy. So high energy photons have a high frequency, the number of times the wave oscillates per second, but they have a small wavelength, the distance between two wave peaks. Low energy photons have a low frequency, but a long wavelength. We want to talk about the distribution of energy for photons that are emitted from something based upon its temperature. Scientists like to talk about an idealized form of an object called a black body. A black body is essentially a thing that absorbs all incoming radiation perfectly without reflecting any away, and this idealization makes it easier to do the theoretical math. It's a bit unfortunate of a name, however, because most colored solids and liquids emit energy almost exactly like a theoretical black body, and in fact, a hot enough black body would glow, making it not even black. But as long as we understand that when we say black body, we just do it because we don't want to worry ourselves with measuring reflected wavelengths, we'll be okay. If we look at the emission spectrum of the sun from the top of the Earth's atmosphere, we see that it has a particular shape, with a peak in emissions right in the visible range, with a fast decline at higher energies and a slow decline at lower energies. Interesting aside, have you ever wondered why humans can see visible light and not, say, microwaves? Well, eyes probably evolved the way they did because that's the most useful part of the electromagnetic spectrum to see in. There are a lot of photons bouncing around because the sun shines so brightly in that part of the spectrum. Anyway, we'd see the same shape if we looked at the emission spectrum of the Earth, but the energy emitted per square meter would be much, much lower, and there would be almost no photons at all emitted in the visible part of the range. Back in 1900, in a breakthrough for what would become quantum mechanics, Max Planck realized that you could reproduce the observed emission spectra if you made some basic assumptions about the way radiation works. And after a little math, he produced what's come to be known as Planck's law. Planck's law looks pretty messy, but the beautiful thing about it is that it allows you to calculate the energy emitted per square meter of a black body's surface at any wavelength, knowing nothing more than the body's surface temperature. All other things in the equation are just constants. I think that's pretty neat. But that's not all. Planck's law applies to a particular emission wavelength. But what if all we care about is total emissions? We can get that by adding up the energy emitted at each wavelength. The proper way to do that, of course, is to integrate the equation over all wavelengths, and I used to do that in my course just to show the elegance of it all. But in my 20 years of teaching, I've learned that students in this class hate it when I do calculus, even if I explain that it's only to reveal the mathematical beauty. And so you're going to have to trust me that the total emissions energy emitting from a black body, pretty much any solid or liquid, is just equal to a constant times the temperature raised to the fourth power. That's the Stephan-Boltzmann Law. And it's pretty impressive to me that you can get such a simple equation out of a fairly messy-looking Planck's law. That's calculus. Temperature has to be expressed in units on an absolute scale, unlike Fahrenheit or Celsius, which have an arbitrary zero value stuck in the middle of the temperature scale. So we'll use Kelvin because it's easy to work with. Degrees Celsius are the same size as units of Kelvin, so to convert from Celsius to Kelvin, all I do is add 273.15. At 0K, everything is at its lowest energy state, so it would be impossible to go any lower, which is why it's called absolute zero. Just in case the Stephan-Boltzmann law weren't cool enough, notice that it's easy to remember the constant. It's 5.67 times 10 to the minus 8. So I just remember it's 5678. Next time you're at a socially distanced party, try steering the conversation to the Stephan-Boltzmann law and casually drop the value of the constant like it's just no thing. And I guarantee you that your friends will think you are as cool as I am. Anyway, notice that the equation allows me to calculate two things. I can determine the energy emitted if I know the temperature, or I can rearrange the equation and find the temperature if I know the total energy per unit area that a black body is emitting. Notice that in this case, I have to take the fourth root of my equation. For those who are rusty on their algebra, taking the fourth root is the same as raising something to the 1/4 power. So you can either use the root symbol on your calculator or just raise your result to the power of 0.25. So, let's say that you want to use your newfound knowledge to impress someone. You could steer the conversation back to energy and ask if they know how many watts per square meter their dog is emitting, mostly in infrared radiation. They'll probably say no, and now's your chance. Dog body temperature is about 101 degrees Fahrenheit, or about 38 degrees Celsius. So, converting that to the absolute scale, we have 311 Kelvin. 311 Kelvin to the fourth power is about 9.35 times 10 to the ninth. Then you multiply that by the Stephan-Boltzmann constant of 5.67 times 10 to the minus 8 to get about 530 watts per square meter. Then you raise an eyebrow and wait for them to be impressed. Now, let's say you're in astronomy lab. You measure the energy coming off of a distant planetoid, not planet, like Pluto, at 0.25 watts per square meter. You might exclaim, that planet is way colder than my dog. But that might not be specific enough for Dr. Nelson. But now you know how to figure out what the actual temperature is. You just divide the energy by the Stephan-Boltzmann constant, then you take the fourth root, and voila! You know that planet is about 46 Kelvin, or minus 227 degrees Celsius. Later, we'll figure out what all this means for the Earth, but that's a good place to stop for now.